One of the most baffling dark openings and the universe's bizarre phenomena remain the focus of intense examination and interest among experts in space, physicists, and other scientists alike. Referred to as dark openings due to their monstrous total weight and gravitational pull, these entities are defined by the absence of visible light and mark a limit beyond which the established rules of physical science cease to apply. In 1916, Albert Einstein speculated about the existence of dark openings as a consequence of his general theory of relativity. For decades, this remained a mechanical speculation until advancements in technology made it possible to identify these phenomena in the 21st century. The 1960s marked a turning point when space researchers discovered the Cygnus group of stars by accident. Among them was a brilliant blue star that emitted high-energy X-rays. This unusual celestial object, circling an unseen companion, challenged regular explanations, until it was made clear that the star was caught in a gravitational embrace with a massive, dark object, Cygnus X1. The clear discovery of Cygnus X1 served as evidence for the existence of dark openings and began a new phase of research. Discovered about 6,000 light-years away from Earth, Cygnus X1 has remarkable characteristics. It is extremely dense and exerts a gravitational force so strong that not even light can escape. This defining characteristic gave it its name, dark opening, which captures the essence of these enigmatic objects. Research results have shown that a smattering of dark openings exist. Estimates imply that the Milky Way galaxy alone may harbor over 100 million such entities. Despite their elusive nature, scientists have identified a number of candidates within our galaxy, with masses ranging from stellar-sized dark openings, formed by the remains of massive stars, to extremely massive ones located in the centers of galaxies. The gravitational impact of dark openings goes well beyond their immediate vicinity, influencing the broader components of cosmic evolution. Surrounding matter that ventures too close to a dark opening faces a fate dictated by its relentless gravitational force. Once past the event horizon, the final turning point, objects are exposed to extreme tidal forces and ultimately consumed by the singularity at the center. This horrific interaction is referred to as spaghettification, where the strength of gravity stretches an object nearing the event horizon to an extreme, twisting it into filament-like structures resembling spaghetti. The dark opening's forces break through the internal bonds that maintain the object's integrity, resulting in its breakdown into a stream of matter that merges with the singularity. Despite their terrifying nature, dark openings serve as essential laboratories for pushing the boundaries of physical theory. They remain shrouded in mystery but inspire an ongoing scientific mission driven by the desire to understand the fundamental nature of space, time, and gravity itself. In the vastness of the cosmos, dark openings remain silent sentinels, urging humanity to explore the unknown and challenge the limits of human understanding. In 2019, researchers achieved a historic breakthrough by obtaining the first clear image of a dark opening, specifically, the one located in the center of the M87 galaxy. This remarkable accomplishment provided crucial insights into the nature and behavior of dark openings. The visual data revealed that dark slits have complex structures, challenging the conventional view of them as empty voids. Through detailed image stitching and analysis, researchers identified three distinct layers within a dark opening. The outermost layer is the event horizon, a critical boundary beyond which gravitational forces cannot be overcome. Once crossed, any object is destined for descent into darkness. Moving inward, the second layer is the photon sphere, where light orbits the dark opening in a state of eternal bondage. Photons trapped here comply with the overwhelming gravitational pull, never escaping the cosmic embrace. At the very center lies the singularity, the third and final layer, where the laws of physics collapse. Here, matter is compressed into an incomprehensible point of infinite density. Within this mysterious singularity, the known laws of the universe no longer apply, launching scientists into a realm of profound theoretical uncertainty. The complexity and variability of dark openings present significant challenges to our understanding. Although they follow a common three-layer structure, each dark opening exhibits unique properties and behaviors that defy traditional classification. Current scientific methods often fall short, requiring innovative approaches to unravel these cosmic behemoths. Since direct exploration is impossible due to extreme gravitational conditions, observation remains primarily indirect. Any attempt to send probes would result in their destruction by the overwhelming forces. Nevertheless, researchers persist in their efforts to uncover the mysteries of these colossal cosmic giants. Numerous theories suggest dark openings originate from collapsed stars. NASA's study of M87's cosmic center has provided compelling evidence for a supermassive dark opening exerting gravitational influence across vast regions of space. Despite the unanswered questions, the pursuit of knowledge continues, fueled by humanity's innate curiosity and a desire to understand. Among the most captivating theoretical implications is the concept of the Einstein-Rosen bridge, more commonly known as a wormhole. This hypothetical structure, predicted by Einstein's general theory of relativity, suggests the possibility of a space-time gateway, potentially connecting distant regions of the universe or even parallel universes. Massive objects warp the fabric of space-time, creating gravitational fields that affect the motion of surrounding matter. Wormholes, if they exist, could offer shortcuts across this cosmic fabric, allowing faster-than-light travel over astronomical distances. However, their stability and practical use remain highly speculative. Radiation, quantum forces, and the intrinsic instability of wormholes raise doubts about their viability as transport systems. Einstein's theory of general relativity imposes limits on travel speed through space and time, implying that even if stable wormholes exist, they may not permit faster-than-light travel. Still, the allure of wormholes persists as a powerful symbol of scientific curiosity and the dream of exploring the infinite. The idea of the Schwarzschild wormhole, named after a pioneering physicist, illustrates the tantalizing concept of cosmic portals and invites humanity to contemplate alternate realities. This journey also fuels the pursuit of a unified theory that connects the scattered domains of gravity and quantum mechanics. At the forefront of this search stands Michio Kaku, a renowned theoretical physicist whose work on superstring theory has transformed modern physics. This theory posits that fundamental particles are not point-like entities, but tiny vibrating strings. Like musical instruments, these strings resonate at specific frequencies, producing the particles and forces observed in nature. Under this paradigm, the universe becomes a grand symphony, with each particle representing a unique harmonic note. Superstring theory offers one of the most promising paths toward a comprehensive theory of everything, seeking to unite all fundamental forces and particles within a single. This revolutionary shift in perspective has not only redefined how we understand the very fabric of reality but also opened the door to exploring dimensions beyond the familiar three of space and one of time. Superstring theory suggests that the universe may contain as many as 10 or 11 dimensions, most of them compactified or hidden from our perception, each playing a crucial role in the orchestration of cosmic phenomena. These extra dimensions could potentially explain the elusive nature of gravity, which remains the weakest of the fundamental forces, yet dominates at cosmic scales. If gravity is able to leak into higher dimensions, it would account for its apparent weakness when compared to electromagnetic or nuclear forces. This idea, while speculative, fuels intense research at the intersection of quantum mechanics, general relativity, and cosmology. In this grand quest, dark openings, once thought to be the death sentence of matter and energy, have emerged as critical tools for exploring the very foundations of physics. They serve as natural laboratories where the most extreme conditions of gravity, density, and space-time curvature converge. What happens inside a dark opening could offer insights not only into the birth of stars and galaxies but also into the nature of time, entropy, and even the origins of the universe itself. Among the many enigmatic aspects of dark openings lies the problem of information loss. According to classical physics, anything that crosses the event horizon is lost forever, its information destroyed. However, this contradicts the principles of quantum mechanics, which insist that information cannot be truly lost. This paradox, known as the black hole information paradox, has sparked decades of heated debate and theoretical exploration. In response, physicist Stephen Hawking proposed that black holes might slowly evaporate over time via a process now called Hawking radiation. This mechanism, rooted in quantum field theory, suggests that particle-antiparticle pairs forming near the event horizon could result in one falling in and the other escaping, gradually draining the dark opening of its mass and energy. Yet, whether this process preserves or erases information remains unresolved, deepening the mystery. As science pushes further into the frontier of dark openings, powerful instruments like the Event Horizon Telescope, gravitational wave detectors like LIGO and Virgo, and advanced space observatories continue to refine our understanding. Each new discovery brings us closer to unraveling the fabric of space-time and answering some of the most profound questions humanity has ever asked. What lies beyond the event horizon? Can information truly survive the journey into darkness? Are wormholes more than just mathematical curiosities? Could they become bridges to other galaxies, timelines, or versions of reality? Though the answers remain hidden, like the singularities themselves, our pursuit of them defines the essence of scientific inquiry, to venture into the unknown, confront the unimaginable, and illuminate even the darkest corners of the cosmos. And in that pursuit, the story of dark openings is far from over. The theory is false in its capacity to explicate mysterious things that are associated with the dark, wormholes, openings, and other exotic solutions to the equations of Einstein's gravity. As the fabric is twisted by strings, the dynamic motion of spacetime results in the development of gravitational anomalies, in topology and singularities. Despite this, the elegance of superstring theories hides their inherent complexity, as it calls for the existence of supplementary dimensions besides the three familiar spatial dimensions and an additional temporal dimension, dimensions that are out of sight. Observing them presents a significant obstacle to human intuition. Still, models such as the fish analogy, living in a lake with only two dimensions, provide a glimpse of the mysterious nature of these more advanced dimensional realms. These have been compacted into additional dimensions, similar to the folding of paper when it is rolled up, still imperceptible on a daily basis. Their influence is felt right down to the material of reality, and the exact nature of these under-the-radar dimensions remains elusive in their conceptual presence. A promising explanation for the oddities and complex structures observed throughout the universe. Additionally, the mathematical foundations of superstring theory have brought about a renaissance in mathematical physics that reveals deep relationships among dynamic mathematical patterns and physical phenomena. The search for a complete theory has sparked the integration of different fields, bringing to light the intricate interaction between the natural and mathematical sciences. Despite its superior beauty and scientific potential, the theory of strings remains unproven, a framework ready for testing and validation. The elusiveness of additional dimensions constitutes a formidable obstacle, relegating experimental verification and bringing superstring theory into the realm of mathematical speculation. Nevertheless, the bold concept of superstring theory still captivates the minds of enthusiasts and researchers alike, enticing the human race to go on a journey of intellectual discovery as we progress further into the unexplored areas of theoretical physics. Under the guidance of the illuminating beacon of superstring theory, we are presented with the vast universe's mysteries, poised at the beginning of a new era of understanding and the task of unraveling enlightenment. Quantum dark opening secrets have long perplexed physicists, representing a significant threat to our comprehension of the universe's fundamental nature. Despite numerous efforts by physicists to solve this mystery, it has remained beyond our reach, an elusive solution that continues to escape our grasp. Edward Witten's description at the Institute for Advanced Study at Princeton referred to superstring theory as the physics of the 21st century that accidentally entered the 20th. But recent developments have incorporated new hope into the search for comprehending dark quantum openings. A number of physicist groups have independently stated a significant breakthrough, that string theory could provide a complete solution to the issue, though within the more restricted setting of 2 dimensions as opposed to the full 10-dimensional model proposed by conventional superstring theory. Nevertheless, this is an encouraging development. The search for an all-out solution continues to deal with the complexities of the situation, presenting significant hindrances to the pursuit of a single theory of everything. It calls us to investigate the darkest corners of the universe's existence, where the lines separating reality from theory become hazy, and the secrets of the universe carry weighty discoveries. Dark spaces carry significant repercussions for our comprehension of reality, testing our very ideas of existence. The interaction between gloomy cracks and other astronomical events, like neutron stars and gamma bursts, reveals the intricate procedures operating in the cosmos. The investigation of dark openings and how they interact with surrounding matter continues to reveal a wealth of fascinating phenomena. One of the most fascinating aspects of these cosmic giants is their ability to warp spacetime with such fervor that they produce ripples, gravitational waves, in the very fabric of spacetime itself. These waves travel away from their source, distributing information about the dynamics of the occurrence, like the collision or merger of 2 black holes, or a black hole with a neutron star. Detection has evolved into a powerful instrument for universe research, especially considering that the initial direct observation of gravitational waves through the Laser Interferometer Gravitational Wave Observatory, LIGO, in 2015 opened a new avenue for research. This new astrophysical window allows scientists to observe the most significant cosmic events, like black holes combining, with unprecedented clarity. As these observations continue to build up, they bring us closer to comprehending the true nature of dark openings, their organization, and their evolution. One particularly puzzling aspect is how matter behaves as it falls into a black hole. Current models suggest that matter undergoes significant change as it approaches the singularity. But questions remain: what becomes of the information contained within that matter? This is referred to as the information paradox, a problem that has baffled physicists for decades. Quantum mechanics states that information about the state of a particle cannot be lost, whereas black holes appear to erase all data that falls into them, putting the fundamentals of quantum theory into question. Solving this paradox remains one of the primary goals in modern theoretical physics. Additionally, the possibility of a connection between dark openings and the overall structure of the universe continues to be an active area of investigation. Some hypotheses suggest that gigantic black holes in the centers of galaxies play an important role in shaping individual galaxies, affecting their development and even triggering star and planetary system formation. The relationship between the dark and these cosmic giants, as well as the majority of matter and dark energy in the universe, is also the subject of close scrutiny. Comprehending the interaction of dark openings with these enigmatic parts of the cosmos may be necessary to unlock many of the universe's greatest secrets. As theoretical and observational capabilities advance, the scientific community finds itself on the cusp of revelations that could redefine our understanding of space, time, and existence itself. The fabric of the cosmos, once perceived as a static stage upon which matter performed, is now seen as an active, dynamic entity, sculpted and stirred by energy, mass, and phenomena that elude classical intuition. Among these phenomena, the enigmatic nature of dark energy adds another layer to the already intricate puzzle. Accounting for the accelerated expansion of the universe, dark energy remains one of the most confounding discoveries of modern cosmology. Its interaction, or potential interplay, with the warped geometries of supermassive black holes and the curled-up dimensions predicted by string theory invites questions that transcend the boundaries of current models. Could it be that what we perceive as dark energy is a manifestation of higher dimensional forces bleeding into our observable realm? Are the apparent voids in space not truly empty, but resonating with invisible structure, shaped by the vibrations of strings too small to be seen, yet too influential to be ignored? This growing confluence between cosmology, quantum mechanics, and higher dimensional geometry hints at a fundamental unity, a deeper law not yet fully glimpsed, but sensed at the edge of mathematical possibility. The very equations guiding string theory begin to whisper of M-theory, a potential theory of everything in which 11 dimensions converge, and strings give way to more complex entities, membranes, or brands, moving like sheets through a multidimensional reality. According to this paradigm, entire universes could coexist as neighboring brands, separated by an infinitesimal fraction of a millimeter in higher dimensional space, invisible, undetectable by ordinary means, yet gravitationally interacting. Some theorists even propose that the Big Bang itself may have been the result of a cosmic collision between brands, sending shockwaves of creation rippling through the newly formed spacetime. In such a framework, dark openings, black holes, are no longer mere endpoints of matter's journey, but gateways, bridges, or even interdimensional connectors, potentially linking disparate regions of space, or entirely different realities. And still, at the heart of this pursuit lies a deeply human desire, to understand, to reconcile paradoxes, and to find unity where chaos appears to reign. The observer is not passive. Consciousness itself becomes a point of inquiry, a mysterious participant in the unfolding drama of reality. As we reach toward the stars and descend into the quantum abyss, we find ourselves equally studying the architecture of the universe and the limits of our perception. What lies beyond the veil of dark openings may not only redefine our science, it may transform our place within the cosmos.